Okay. Let me once again continue from the point where we have left in my last lecture. In my last lecture, I have shown just by applying consolidation, one dimensional consolidation theory, we have developed a mathematical expression, a relationship between t and u, where t is the time factor and u is the degree of consolidation. U is the degree of consolidation. What is degree of consolidation? That is actually, suppose under certain loading the expected settlement is suppose 100, and if at any time settlement is completed suppose 20 millimeter, then degree of consolidation is 20 by 100, 20%, like that. So, degree of consolidation u defined is like that, and another is time factor. Time factor is a non-dimensional term again, which is equal to C v, coefficient of consolidation time t, duration time duration t by h square. H is the longest distance of the water particle to travel for dissipating the pore pressure. So, that t versus u relationship mathematically we have shown by applying one dimensional consolidation theory. Now, let us see how to utilize this, or how to for calculation of time settlement, and also how to determine those C v value also, which is very important in estimating the consolidation settlement, particularly for finding out the time consolidation settlement. C v is very important. So, how to determine C v? So, this actually I have shown this expression in the previous lecture, which is obviously relationship between u and t. Those m and other things they are actually something parameter defined there, and now this expression if I use, and in this actually there is a small m which is equal to 0 to infinity, and for developing of this one dimensional consolidation settlement we assume m equal to 1. And what is m actually? Now, I can show you schematically here. We have shown this different pressure distribution, pore pressure distribution, this is 1, this is 1, this is 1, like that 4, 5 pressure distribution, pore pressure distribution we have shown, and this is the one we have said that we have assumed that uniform pore pressure distribution. That means, the top of the layer and bottom of the layer, if I consider u I here and u 2 here, the ratio of this m is the ratio of this pore pressure at the top divided by pore pressure at the bottom, u 1 by u 2, and that is taken as 1, and for this expression. But this similar treatment can be done with different values of m equal to 0, when it will be m equal to 0, when this is the one, that means it is a newly deposited soil. So, pore pressure will be 0 at the top, at the bottom it will be maximum, the ratio becomes 0, the m equal to 0, then there can be another relationship. Loaded foundation at close to the surface it will be maximum, and at a particular depth is 0. So, here actually m will have the value infinity. So, then we will get another set of relationship, and then in normal case that at a embankment loading, then in that case you will have lesser value of pore pressure here and more value of pore pressure at depth. So, this one m equal to less than 1. So, if I apply that one, you will get another set of solution, and here actually at a particular depth thick layer is there, in that case pore pressure will be here maximum, and at a greater depth it will be very less. So, in that case ratio will become ratio of m, or ratio of these two pressure which is defined as m will be greater than 1. So, if I use that m, we will get another solution, but so far we are actually for undergraduate level particularly we are actually it will be enough actually if we can understand the case with m equal to 1, that means pore pressure distribution uniform within the layer, and that means this is the case. And if this is the case, then you can see there are different plots are given, time factor this is u t, and this is degree of concentration u. T versus u plot by mathematically develop the solution and finally plotted T versus u, and this is giving for different values of, you can see m equal to 0.5, m equal to 0, this is for 0.5, this is for 0, this is for 1, this is equal to 5, this is equal to infinity, but we will be working with 1. So, this is the 1, this is the T versus u corresponding to m equal to 1. So, we will work with that, and again if you read this value and graphically if you put, then you can see u versus t, there are certain values. So, which I will show in the next slide also. You can see here I have written once again u and t, u 0, t equal to 0, u equal to 10, t equal to 0.008, u equal to 20, 0.0032, 31, u equal to 30, 0.071, u equal to 40% actually 0.126, 50%, 0.197, 60%, 0.287, 70%, 0.405, 80%, 0.565, 90%, 0.48. So, this is the T versus u data. This data if you try to fit, it actually approximately fit in two equations up to 60%, that means less than 60%, the T can be approximately fitted by this equation, T equal to pi by 4 u square. Okay. This is one up to 60% when u less than 60%, and another equation when u greater than 60%, this equation no longer valid, it will give error. So, we have another equation for u greater than. So, this is the 1.781 minus 0.933 log 10 base 100 minus u. So, these two things actually you need to remember time to time for calculation. This may be required because you know the u, from u you have to find out the time factor, and once you get the time factor t, you know Cv T by h square. So, if you know the soil property, if you know the thickness of the layer, so T how much time will take to consolidate, that much percentage of degree, that much degree of consolidation we can find out. So, this equation, these 2 points, 3 ways can be used. One, actually directly one can read the chart, you know the degree of consolidation 50%, from the chart you find out what is the T. Another way, generate data for T versus u, then you fit. So, if you can directly use the equation to find out the T, if you know the u, find out T from this equation, and so these 2 ways actually one can find out T versus u. And now, when there is a layer, there may be situation only one side is rock and one side is pervious soil. So, water will flow in one direction. Sometime there may be layer and this side, both side actually pervious soil. So, flow will be in the both direction. So, accordingly, whatever equation we have used, T equal to Cv T by h square, this h actually the longest distance the water particle to move to dissipate the pore pressure. So, if this is impervious, then to dissipate pore pressure from here, the water particle has to move this much distance. So, this much. So, in that case h become this. So, longest, though soil particle here to dissipate will travel this much distance, but at this point it will travel this much distance. So, longest path is h. So, that means, if there is a drainage is like this, that means one way is impervious and other side is pervious, then longest path will be the thickness of the layer. Whereas, if you have both side drainage, then the longest path the water particle to move for dissipating the pore pressure will be half, because if water particle is here, it will try to go this direction instead of going this direction. So, never be more than half. So, maximum point at the midpoint, either it can go this side or go this side. So, because of that, when drainage is in the both side, then the longest distance water particle to travel for dissipating the pore pressure is half the thickness of the layer. So, that is the thing is mentioned here. If the soil above and below the consolidating layer are pervious, the water under pressure in the layer will travel either that means water under pressure, because within this, because pore pressure, because why? Because it is in the under pressure, because of that pore pressure is developed. So, layer will travel either upwards or downwards. This case is known as two-way drainage. So, that means when pervious layer at both at top and bottom, that is called two-way drainage, and when there is a two-way drainage, the maximum length that a water particle needs to travel for dissipating pore water pressure from the consolidating layer, that is equal to thickness of the layer divided by 2. And we in our analysis we have considered thickness of the layer as 2h. So, your drainage path will be h, and this is schematically shown in this. You can see this is permeable and this is also permeable. So, water particle from here maximum distance travel, if it goes, whether it goes this way or this way, the distance is still h, but if the water particle is here, it will never go this way, because before that if it goes there, it will be faster. So, they will try to release faster because it is under pressure. So, always because of this, you have maximum or longest travel path for water is the thickness, half the thickness of the layer. Whereas, if one side is impervious and other side is permeable, then water particle will dissipate from different points in one direction, but maximum distance to travel from here to here actually. So, that is the one, that means that is called one way drainage, and for one way drainage your longest path water particle to travel to dissipate the pore water pressure is equal to the thickness of the layer. So, that is the thing that this two symmetrical diagram, two way drainage, this is two way drainage, or it is called double drainage, and this is one way drainage, or sometimes called single drainage. Okay. So, double drainage actually their h will become half the thickness of the layer, when single drainage then it will be thickness of the layer itself will be the h. So, this is same thing repeated here, whatever I have just told. If one of the soil layers either above or below the consolidating layer is impervious, water will travel in one direction, and the case is known as one way drainage. The length of drainage path, that is the longest path a water particle need to travel for dissipating pore pressure for this case is h. It should be 2 h actually, since we have considered or it will be thickness of the layer, we can say thickness of the layer, which will be equal to 2 h. Okay. So, because we have considered this thickness as 2 h, and if it is one way drainage, that is closed here. Now, T versus U, you know, and now T versus sample thickness observation. It is seen that for a particular pressure increment applied during a consolidation test, the compression of the test sample is plotted against the square root of time versus sample thickness. If it is plotted, then we get a curve like this. Initially a small curved portion, then for a sufficiently long straight portion, and then again there is another curved portion. So, they have different name, different location. This is actually initial compression, either it is elastic you can say, or particle adjustment, breakage of particles etc. because of that this small portion, and when those adjustment is established, then consolidation will take place. B to C, this is the consolidation and primary consolidation, and this one will be secondary consolidation, and many other things can happen here. So, there are 4 parts. So, we will explain one by one what are those. You can see the curve is seen to consist of 3 distinct parts A B, B C and C D, and A B is initial compression or frictional lag. So, because of this it is in a ring, sample will be prepared and it will be loaded, and then compression will be observed. So, initially you will have a slower rate. Initial compression is a small but rapid compression sometime occur at the commencement of the increment, and is probably due to the compression of any air present, or to reorientation of the sum of the larger particles in the sample. In the majority of the test, this effect is absent and points A and B are coincident. Initial compression is not considered to be due to any loss of water from the soil, and should be treated as a zero error for which a correction is made. That means, you have the curve like this, initial portion, and then it will be straight. So, this portion it can be taken as a error or correction. So, this is what is happening. Consolidation means when the volume change is taking place, same amount of volume of water is going out. Okay. Here actually up to this B point, we are considering it is there is a no movement of water. It is because of many other things which is listed here. And B C is the primary compression, that is whatever consolidation mechanism we have explained. All the compression in this part of the curve is taken as being due to the expulsion of water from the sample, although some secondary compression will also occur where the pore pressure has been reduced to a negligible amount. It is assumed that 100% consolidation has been attained. That means, when in the consolidation setup, you have applied load, and by definition of completion of consolidation is what? When you apply the load, then within the soil pore pressure will develop, and when after that we will keep it for a longer time, then pore pressure will dissipate, and slowly pore pressure, excess pore pressure will be reduced, and when the excess pore pressure is coming to 0, that time we say it is a completion of pore pressure, completion of consolidation. But here sometime from a 99% to pore pressure 99% to 0% or 100% dissipation, 99 to 100% dissipation may take very long time. So, because of that, sometime when it pore pressure become negligibly small, some 98%, 97%, still we may consider as a completion of consolidation, otherwise you have to wait for a long time. And then this is B C part, and C D part is a secondary compression. The amount by which this effect is evident is a function of the test condition and can hardly be related to any in situ value. So, this is secondary compression theory is different, we will not discuss right now. We will try to discuss this handling that primary consolidation settlement, how to this observation, how to utilize for finding out some soil parameter relating to compressibility of soil. So, to evaluate the coefficient of consolidation, it is necessary to establish the point C. That means, we have shown there that sorry, we have shown that this is the point, there is this one and then this one and then this one. So, between B to C, that means C point has to be established. Why? Because this is end of 100% consolidation, correspond 100% consolidation, but it is difficult from a study of the test curve to fix C with accuracy, and a procedure in which the test curve is fitted to the theoretical curve becomes necessary. So, theoretically we observed and based on that some adjustment can be done to find out approximately this behavior or this value. So, one such technique was proposed by Taylor, who first observed the theoretical curve u against root t plotted, u versus root t is plotted in uniform excess pore pressure distribution. The curve will be like that shown in the figure A in the next slide. So, I will come to that figure. U up to values of u equal to about 60%, the curve is a straight line of equation. So, that is equation is this u equal to 1.13 under root t. Up to values of u equal to 60%, the u versus t is a straight line, but if this straight line is extended to cut the ordinate of u 90%, the abscissa of the curve is seen to be 1.5 times the abscissa of the straight line. This fact is used to fit the test at theoretical curve. So, we have observed something in the test results. Now, it is observed with theoretical curve u versus t root t, and then it is seen that up to 60% is straight line and beyond straight line is beyond 60% is a curved one, but at 90% which is close to the 100%, that point we have seen there is a relationship between this original curve and the straight line. So, it is ratio is 1.15. So, this point is of this observation will be utilized. So, to fit the curve and find out CV. You can see here this is the one observation is given initially, root time factor versus degree of consolidation u plotted like this, and up to 60% it is perfect straight line and then started deviating from the straight line, but it is 90% consolidation. You see the abscissa whatever value was here and whatever value on the curve, actual curve, it is 1.15 times the abscissa of the straight line. At this straight line at 90%, whatever initial curve you have got up to 60%, that one we extend up to 90%, whatever value you read, suppose x, then actual curve on that point will be 1.15 times x. So, this is the important observation to be used for utilizing and find out the coefficient of consolidation CV. So, you can see now the test curve in the test curve. So, generally initially there will be a curve 1 and then this will be like this, it will come root time versus sample thickness if you plot, and then if there is a curve, then we can the straight portion we can extend and this one can be taken as a 0 start point of the consolidation, and if the soil does not have this initial portion, then you are getting correctly 0 point, but if it is not, if there is a curve, then the straight portion can be extended to intersect the x axis here, that will be a starting point of the consolidation. And now, this curve is whatever test data we have, based on that you can draw the curve, and like this you can draw the curve, and after drawing the curve what we can do, since whatever observation we have made that abscissa on the straight line will be equal to but abscissa on the curve will be equal to 1.5 times the abscissa on the straight line. So, we can take 1 or 2 points from here, and you can take 1 or 2 points on this suppose this is 1 and we read value x, you multiply by 1.15 and establish a point here, then join this to this and extend it. Okay. Then after extending this one, it will intersect the original curve somewhere here. Once they intersect somewhere here, that since it is at 90%, that is the observation we have seen 1.15 times, and now we are doing reverse based on we have observed this one. Now we consider this as a fact. So, we have taken a value on the curve and we have multiplied by 1.1.5 intersect the curve. So, that intersecting point what will happen here actually 90% consolidation we have got this observation. So, when you have reverse you have done and intersected here, that means that point will represent the 90% degree of consolidation. So, this point, so this become corresponding point to 90% consolidation. So, I can now I can find out this is original thickness and this is 90%. So, from here actually you can find out this 90%. So, degree of consolidation 90%. So, T 90 you can find out and then relate and then we can find out the CV by using the relationship we have. Now, based on this, so this point, that means you are getting here by this construction you are getting U 90. Okay. Once you get the U 90, so once again whatever I have mentioned just repeat. With the test curve, a corrected 0 must first be established by projecting the straight line part of it. So, that means if you have the curve like this, so you extend the straight portion, you will get, though the curve started here, but you can consider start of consolidation here. Line of the primary compression back to cut the vertical axis at E. So, that means this is the point E. A second line starting through E is now drawn such that the abscissa on it are 1.15 times corresponding value on the abscissa on the curve. That means, from here I will read the value, suppose this is x and then I multiply it by 1.15 and then I get the point here, and from here to here I join and this curve will intersect somewhere here. So, that is the thing is done. Abscissa on it are 1.15 the times the corresponding value on the laboratory curve. At the point at which this second line cuts the laboratory curve is taken to be the point representing 90% pi metric consolidation. So, this line when intersected, because previously you have observed that at 90% this is the thing happening. So, now we are reverse we are doing, we are drawing the line intersecting the curve, where it is intersecting that we are considering as 90% consolidation. So, U 90 you are getting. So, to obtain CV, T 90 is first found from the theoretical curve that fits the drainage condition, T 90 is determined from the test curve. So, you can see now you can see now this is a relationship we know, you know T equal to CV T by H square. So, if I want to find out CV equal to T H square by CV, and C we want to find out CV which can be considered as the constant, and we have got this I consider, sorry, this is not capital T, this is small t. So, T into H square by CV, sorry, this is actually T, this is small t. So, this T corresponding to 90%, since we have already got our T, this also 90%. So, T 90, that means time required for completing 90% consolidation we can find out from this expression. So, for this what we need, we have to find out T 90. So, T 90 how you have got, how you will get, you have got U 90% and from there corresponding T 90% we can get. So, either way, so if you read from the graph T90 and if you get T90 and if you know the thickness, then you can find out the CV. So, time factors corresponding to 90% degree of consolidation is 0.48. If you go back to the chart, you will see that when u is 90, then t equal to 0.48, or you can use second equation that t equal to 1.781 or something minus 0.933 log 10 base 100 minus u. If you use this equation also, in this equation u equal to 90%, then t will become 0.48. So, you can express the 90%, since you have used 90% corresponding to 90% degree of consolidation. So, this is T90 is 0.48 h square CV and this is T90. So, T90 can be read from the graph. So, CV can be obtained from this. So, this is the one way, that is called root time method. So, determination of CV value from the consolidation test, there are a number of methods are there. This is called root time method. This is called root time method. That means, I can show you the previous slide. This is actually, you can consider this is as a laboratory data and this side is square root of time and this side is a sample thickness. So, from here actually from this plot you can read. So, we have got intersection. So, T90 you will get from the test here and U90, then corresponding T90 I can get from the relationship between T and U. So, once you get T equal to CV T by H square. So, when you carry out test, H is known, T we are getting from here and T you are getting from this relationship. So, only unknown is CV. So, CV can be determined like this, that is by root time method, and so this is one method, and we of course, I will discuss one or two methods again later on. So, this is the way one can find out the CV, and of course, this relationship can be utilized to find out the time consolidation. That means, we know how much we know the certain total consolidation amount, but if you want to know time required to find out time required to consolidate 50% or 60% or 70%, then we need to utilize those expression. How to utilize that, we will see in the next class. I will stop here. Thank you.